Okay, students, now we'll speak about the power in a resistive circuit. Power in a resistive circuit. For that, let me have a simple circuit diagram with one cell and a resistor. Let the resistance of the resistor be R and the potential of the battery is V. Then there will be a current flowing through this wire. Let's say it is I. Then we could say power, it is the work by time. Power is work by time. And as we know, potential and work. As the definition of potential difference or potential was denoted by the letter V, and we have learned that V is equal to W by Q. We have learned V is equal to W by Q. Then I could say W is equal to V into Q. From the definition of potential, we know V is equal to W by Q, and we could say W is equal to V into Q. Then if I am substituting W as V into Q, we could write power as P is equal to VQ by T. Can you say what is Q by T? Q by T is rate of flow of charge, that is current. We know I is equal to Q by T. Therefore, Q by T. Therefore, I could write power is equal to VI. Power is equal to VI. It is one expression for power in a resistive circuit. Voltage into current. And if I am using Ohm's law, we know V is equal to IR. If I am using Ohm's law, V is equal to IR. In this situation, we could write IR into I. Instead of V, I am substituting IR, means we could write IR into I. IR into I, it is I square R. IR into I, it is I square R. Therefore, P is equal to I square R. This is another important relation. Then we could write, instead of I could write I is equal to V by R. And if I am replacing I as V by R, we will get P is equal to V into V by R, that is V square by R. This is another important relation. Therefore, power in a resistive circuit, we could conclude it like this. Power in a resistive circuit is P is equal to VI, that is equal to I square R, that is equal to V square by R, and it is equal to W by T. Okay, therefore this is the expression for power in a resistive circuit. Okay, the SI unit for power, it is watt, and there are some other units that we are commonly using. It is kilowatt, and kilowatt means it is 10 raised to 3 watt. Then it is megawatts means it is 10 raised to 6 watts. And there is horsepower, HP. One horsepower is 746 watts. These are some common units used for measuring power, and this is the SI unit of power. Okay, you should remember this also. Then if we are going back to our series combination, in series combination we know current is same, and now we know P is having three expressions: VI, I square R, V square by R. And since current is same, I am using power's expression as I square by R. I could use, it's not I square by R, it is I square R. I square R. I could use power's expression as I square R. Since I is constant, I could write power, it is directly proportional to R. Since I is constant in all resistors, power can be written as directly proportional to R. Therefore, let's say the power in first resistor is P1, the power in second resistor is P2, and the power in third resistor is P3. I could write P1 is to P2 is to P3, that will be equal to, since it is P proportional to R, I could write R1 is to R2 is to R3. You should remember this in the case of power. And if you need the power of first resistor, power across first resistor, we could write P1 is equal to I square R1. Likewise, P2 is equal to I square R2 and P3 is equal to I square R3. This equation is important and you should remember in series combination power is directly proportional to resistance. Okay. Then let's move in parallel combination. In parallel combination, you could clearly see the voltage is constant in parallel combination, and since the voltage is constant in parallel combination, let me use the relation of power as power is equal to V square by R. I am using this relation because resistance is always constant, then in parallel combination the voltage is also constant. Therefore in this case we could clearly see, that is in parallel combination we could clearly see power is inversely proportional to resistance. That is, as the resistance is increasing, the power consumed will decrease. As the resistance is increasing, the power consumed will decrease. Therefore, I could write P1 is to P2 is to P3 is equal to 1 by R1 is to 1 by R2 is to 1 by R3. Or if there is two resistors, I could write P1 by P2 is equal to R2 by R1. Okay. Then from this I could write power across first resistor is P1, across second resistor is P2, across third resistor is P3. I can write P1 is equal to V square by R1. Likewise, P2 is equal to V square by R2 and P3 is equal to V square by R3. Okay. Then you will have to remember this situation in parallel combination of resistor. In parallel combination of resistor, power is inversely proportional to resistance. That is, P1 is to P2 is to P3 equal to 1 by R1 is to 1 by R2 is to 1 by R3, or P1 by P2 equal to R2 by R1. Okay, remember this also. Now, as you know about power, power is VI I square R and V square by R. Let's speak about the heat developed in a resistor. Heat developed in a conducting wire or heat developed in a resistor. The heat developed in a resistor will be equal to the work done in the resistor. Heat developed in a resistor will be equal to work done during the charge flow. And as we know from the above equation, we know work is equal to V into Q. And since work is equal to V into Q, I could write it as V into Q. Then I could write work is, power is work by time. Therefore, work is equal to power into time. Work is equal to power into time, and we know power is VI, I square R and V square by R. I could write power into time, work as power into time, and if I am replacing for power as VI, we could write VIT. If I am replacing power as I square R, we could write I square RT, and if I am replacing power as V square by R, I could write V square by R into T. Therefore, these are the expressions for heat developed inside a conductor. These are the expressions for heat developed inside a conductor. You should remember that heat developed will be equal to work done, and that is equal to V into Q, power into time, VIT, I square RT and V square by R into T. This is otherwise called as Joule's law. You might have learned in your smaller classes Joule's law, heat developed, and the SI unit of heat is Joule. SI unit of heat is Joule. And you should also remember the CGS unit. The CGS unit of heat is calorie. Calorie, and 1 calorie is equal to 4.2 joule. Remember this also, it is very important. Okay students, now let's discuss some important sessions in power. Some important sessions in power. For discussing about that session, let's have a bulb over here. Let's say this is a filament lamp, and in this filament lamp it is written 220 volt. It's not 220 volt. Yes, it is written 220 volt 40 watts. On the filament lamp it is written 220 volt and 40 watts. And if you are seeing any electrical device over which the voltage and watts is written, then what you should understand is the rated power. The rated power is 40 watts. The rated power is 40 watts and the rated voltage is 220 volt. That means if you are giving a voltage of 220 volt, then it will consume a power of 40 watts. If you are giving a voltage of 220 volt, then it will consume a power of 40 watts. അതായത് 220 watts കൊടുത്താൽ 40 watt power consume ചെയ്യും. 220 volt voltage കൊടുക്കുകയാണെങ്കിൽ 40 watt power consume ചെയ്യും. Okay, then can you find out the resistance in this? What's the resistance of this filament lamp? By getting these two ideas, we could find out resistance. In order to find out resistance, let's say we know P is equal to V square by R, don't we? Yes, we know P is equal to V square by R. We're going to use this expression, and from this expression it's clear that we could write R is equal to V square by P. We could write R is equal to V square by P. Then what is V square? It is 220 square divided by 40. 220 square divided by 40. It will be 484 ohm. You should calculate this and we'll get 484 ohm. That is, the resistance will be 484 ohm. Then if it is connected to a potential source of, let's say, 110 volt, then what will be the power consumed? If it is connected to a potential source of 110 volt, what should be the power consumed? In this case, we could say the power consumed will be proportional to the voltage consumed. That is, the consumed voltage will depend on the power consumed, or will affect on the power consumed. Then in this case, I am saying the consumed voltage is what? The consumed voltage is 110 volt. The consumed voltage is 110 volt. And let me try to formulate a relation for this. It will help you in solving many problems. Power consumed. For that, let me try to visualize that situation. That is, the rated voltage is 220 volt. The consumed voltage is 110 volt. The voltage that the bulb is consuming is 110 volt, but it is written over it the rated voltage is 220 volt. Okay, then the rated power is what? 40 watts. Then by this relation, that is by P P is equal to V square by R.